Today I will be presenting on quantum computational chemistry, or how one can use quantum computers for computational chemistry. Computational chemistry involves leveraging the computing power of computers such that one can accurately predict fundamental physical properties of useful molecules, and the more useful the molecules are, the larger and complex these molecules become. For example, one can find out the electrochemical properties of various electrolytes on the surface of calcium atoms, and this is useful for the development of calcium ion batteries. Now, to find out the ground state energy of a molecule, one has to solve the electronic structure problem, where the Schrodinger equation defining this problem is shown here. The corresponding molecular Hamiltonian contains both nuclear and electronic terms, where, by using the Born-Oppenheimer approximation, the problem can be simplified such that one has to solve only for the electronic wave function using only the electronic Hamiltonian. Now, a variety of methods exist for finding the ground state energy of a molecule, such as Hartree-Fock, coupled cluster, and so on. And these methods provide increasing accuracy but at high computational cost. This is because the size of the wave function increases exponentially with increase in the number of bases. For example, Hartree-Fock scales as n to the power 4, where n is the number of basis functions being considered. Quantum computers promise to find out such useful properties such as the ground state even faster than supercomputers, but it is based on the fact that the quantum computers will be error-free, that is, fault-tolerant quantum computers, or FTQC. But due to today's technological limitations, the present-day quantum devices are error-prone and are known as NISQ, or Near Intermediate Scale Quantum Devices. Thus, the aim in this project was to find out whether one can obtain ground state energies of a molecule using such NISQ devices. This is important because it, when one knows the procedure to find the ground state energy in NISQ devices, it can be easily implemented on fault-tolerant quantum computers when they become available. Now, extensive research in the field of computational chemistry has led to the development of various user-friendly software packages such as Gaussian, PyQuant, PySCF, etc., which have a fixed set of procedures to find out the ground state energy of a molecule. For example, by specifying the level of theory and basis and knowing the atomic coordinates, one can find out the ground state energy for water molecule. But such a straightforward procedure is not present when one thinks of finding the ground state energy on a quantum computer. In the upcoming slides, I will highlight how one can do so. Before that, one must know some of the basics related to quantum computing. Now, at the heart of a quantum computer is the qubit, or the quantum bit. It is known that a classical computer is composed of silicon-based transistors which store and compute data in terms of 0 and 1. These zeros and 1 are known as the bit, or in this case, the classical bit. A qubit, similarly, is composed of the states ket0 and ket1, which belong to the complex linear vector space. Physically, one can think of a qubit as a two-level atom being composed of the ground and excited state, where the ground state corresponds to ket0 and the excited state to ket1. Thus, a qubit can be shown to be in a linear superposition of the states ket0 and ket1, and when one measures such a state, the entire state collapses to either ket0 or ket1. This is in complete contrast to a classical bit, which can exist only in the states of ket0 or in the states of 0 or 1. Now, to perform operations on a computer, one has to manipulate the bits, and this is done using application of gates. For example, to transform 0 to 1, we apply the NOT gate. Similarly, in a quantum computer, one can transform the qubit state ket0 to ket1 and vice versa, where these are their corresponding matrix forms. To do this, one can define a quantum gate which will perform these necessary transformations. and the quantum gate is said to have the corresponding matrix form. This X is known as a Pauli gate. This is similar to changing the direction of a vector by applying a linear operation on it. Z and Y are other such Pauli gates which perform similar operations. Now, the gates shown in the previous slide deal only with single qubits, but the necessity may arise to manipulate multiple qubits. One such gate is a CNOT gate, which acts on two qubits, where the qubit label Q0 is the control and the qubit label Q1 is the target. The CNOT gate acts such that it performs an X gate, that is flips 0 to 1 and 1 to 0 for the target qubit if and only if the control qubit is in the state 1, and the CNOT gate has the corresponding matrix form. Now, to implement a problem on a computer, one has to formulate in it the problem in terms of zeros and ones, because that is how a computer stores and manipulates data. But our electronic problem given by the Slater determinant is not present in such a form. Thus, one requires a formalism such that our electronic problem can be easily implemented on a quantum computer. The second quantization is one such method which in which the Slater determinant is written in the occupation number vector F, and the occupation number vector can be manipulated by using the fermionic creation and annihilation operators, where the fermionic creation operator AP dagger acts such that it creates a state 1 signifying the presence of an electron, and the annihilation operator AP acts such that it creates a state 0 signifying the removal or absence of an electron, and these operators follow the fermionic anti-commutation. Thus, by using the second quantization, one can convert our electronic Hamiltonian into the second quantized form, where each one-body term consists of two fermionic operators and each two-body term consists of four fermionic operators, where HPQ and HPQRS are the one and two-body integrals respectively. Now, the Hamiltonian in the second quantized form can be implemented on a classical computer since it deals with electrons, but a quantum computer deals with qubits. Thus, we must transform our electronic problem into a qubit 1. For that, we require to use a mapping scheme known as the Jordan-Wigner mapping scheme, in which we define a qubit creation operator QJ dagger, which converts the state gate 0 to gate 1, and a qubit annihilation operator QJ, which converts the state gate 1 to gate 0, where the J denotes the position of an electron in the given qubit state, and gate 0 and gate 1 denote the absence and presence of electrons respectively. Hence, Qj and Qj dagger can be thought to be quantum gates, which can be expressed in these given matrix forms and further expanded in terms of the Pauli X and Y gates, which are the gates implemented on a quantum computer. Now, fermionic operators follows anti-commutation, but the qubit creation and annihilation operators do not anti-commute. To solve this, one notes that xz and zx anti-commute, and similarly the Pauli y and Pauli z gates anti-commute. This is used to write our fermionic operators in a form such that we apply appropriate number of z gates before the qubit creation or annihilation gate, such that we can write our fermionic creation and annihilation operators as represent as a summation of all our Pauli gates in accordance with the anti-commutation principle. Thus, some of the terms in the second quantized Hamiltonian can be written in terms of our qubit gates, and the total Hamiltonian itself can be written as a summation of all our Pauli gates. Hence, we can employ our electronic problem on a quantum computer using the Jordan-Wigner mapping. Now, after this, to find out the ground state energy of a molecule, an algorithm has to be adopted. From the various kinds of algorithm available. Here we have chosen the variational quantum eigensolver. The variation quantum eigensolver acts using the variational principle, where h is our Hamiltonian in the qubit form and psi is a parameter-dependent trial wave function. To obtain psi, we create a quantum circuit by suitable combination of quantum gates, and this quantum circuit is itself parameter-dependent and is called the ansatz U. Q acts on a reference state which is derived from the chemical problem under consideration. Thus, operation of U on the reference state gives us the trial wave function. Expectation value of the trial wave function can be calculated using the Hamiltonian obtained using Jordan-Wigner transformation. The energy expectation value is dependent on the parameter theta, which is updated onto a classical computer. The classical computer employs suitable optimization algorithms such that a new parameter value is obtained, which is again updated onto our quantum circuit. The more suitable parameter values thus provides a new, better optimized trial wave function, and accordingly a new energy expectation value is obtained. This process is repeated until a suitable ground state energy is obtained. Using the entire procedure highlighted in the previous slide, we implemented our VQ calculation using IBM's Qiskit framework such that we obtain the ground state energies of molecules on the state vector simulator. The state vector simulator is a classical machine imitating the behavior of a quantum hardware, where being a classical machine, it does not have any of the errors associated with a quantum machine. Thus, we were able to find out the ground state energies of molecules from hydrogen to water, and these ground state energies were in good agreement with the ground state energies obtained on a classical computer using CCSD level of theory. Here, we face the problem that when the qubit requirement became of 16 qubits, such as for molecules methane onwards, the energy values could not be obtained due to high computational cost. To solve this, we used the approximation of removing the unoccupied spin orbitals such that the qubit requirements came down, and this in turn gave us the ground state energies for molecules ranging from methane to oxygen as well. Here, due to our approximation, the ground state energies deviated more from the CCSD values, but it still acts as a proof of principle that one can find out the ground state energies of molecules requiring qubits as high as 14, provided there is suitable number of qubits. Also, the high accuracy of our VQE for molecules ranging from hydrogen to water shows that one can VQE is an accurate method when compared to our classical techniques. Next, we implemented this same method on real quantum hardware such that we were able to find out the ground state energies of hydrogen and lithium hydride. These energies deviated more from the state vector values because of the errors associated with the quantum machine. Furthermore, since we had access to 7-qubit machine, we used a different kind of mapping known as a parity mapping such that we could bring down the qubit requirement by 2 more qubits. This allowed us to simulate BeH2 and water molecules as well. It is interesting to note here that this brought down the qubit requirements of hydrogen and lithium hydride from 4 and 6 to 2 and 4 respectively, and this in turn improved the deviation of the VQE values from the state vector values. This is because a reduction in the number of qubits led to a decrease in the circuit depth on the VQE algorithm, and which in turn reduce the errors associated with the quantum calculation. Concludingly, I was involved in another project where we worked to propose that cobalt and TMXenes are a promising anode material for sodium ion batteries. Thank you.